This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on optimization word problems. Our first question is that a farmer wants to build a three-sided fence to enclose a pen for his chickens. The fourth side will be his barn. He has 120 feet of fencing. How should he design the pen to maximize the area for his chickens? We're going to assume he's going to build a rectangular pen. The barn is in blue, so there will be three sides for this pen, and these three sides can total no more than 120 feet. So let's give them names. We'll call this side X, and this is the same thing. This is also X, and that's Y. So those three pieces together, X plus Y plus X, has to be 120 feet. X plus Y is 120. 2X plus Y is 120. This enables me to solve for Y in terms of X, subtracting 2X from both sides. Y is 120 minus 2X. Now our goal is to maximize the area. The area of this rectangle is X times Y. We're going to want to maximize X times Y, or maximize X times 120 minus 2X. So this is the function we're trying to optimize or maximize, 120x minus 2x squared when we distribute. We're going to proceed by finding a critical value. Critical values will be where the first derivative is 0 or where the first derivative does not exist. First derivative is 120 minus 4x, setting that equal to 0. 4x equals 120, x is 30. So 30 is our critical value. Now is that a minimum or a maximum? We could use the first derivative test, we could use the second derivative test, we can even do a sort of absolute min and max kind of argument, but I argue here the second derivative is easy. The second derivative is negative 4. So the second derivative is always negative 4, which means it's always concave down, which means it will have an absolute maximum on the interval from minus infinity to infinity. This indeed will give us our absolute max. So the area will achieve a maximum when x is 30 feet. So what is y and what is that maximum area? Well, x is 30 feet. We showed earlier that y was 120 minus 2x, or 120 minus 2 times 30, or 60 feet. So x is 30 feet, y is 60 feet. So our maximum area is 30 times 60. 30 times 60, or 1,800 square feet. So our conclusion is that the maximum area is going to be 1,800 square feet when x is 30, when these two sides are 30 feet, and y is 60 when that one long side is 60 feet. Our next question looks at a company manufacturing television sets, and we're given the price-demand equation of P equals 200 minus x over 30, and we're told that the domain on x is from 0 to 6,000. How do we find the maximum revenue? Revenue is the number of items times the price per item. Revenue is x times P. We have our function P up here, 200 minus x over 30. So revenue is x times 200 minus x over 30, distributing 200x minus x squared over 30. And this is the function we want to optimize, maximize, to find the maximum revenue. So we'll take the first derivative of this function, which will be 200 minus 2x over 30. That, of course, is r prime. Let me fix it. So we have r prime of x is 200 minus 2x over 30, or 200 minus x over 15. We want to take the first derivative and set it equal to 0. So that'll give me x over 15 equals 200. Multiplying both sides by 15, we get x is 3,000. Now, how can I convince you that this is a maximum? And I will argue we're given an interval. We're told x ranges from 0 to 6,000. Those are the endpoints. And we're going to approach this time like an absolute max. We're going to check it at the endpoints and at the critical point. Whichever one is the highest is the absolute max, whichever is the lowest is the absolute min. So we've got these three numbers. X is 3,000 is our critical value. Our revenue function is x times p, x times 200 minus x over 30, 200x minus x squared over 30. Plugging in 0, 200 times 0 minus 0 squared over 30 is, of course, just 0. Plugging in 3,000, 200 times 3,000 minus 3,000 squared over 30 gives us 300,000. And then plugging in 6,000, 200 times 6,000 minus 6,000 squared over 30 also gives me 0. So we approach this like an absolute max. And we'll notice that this function here, our revenue achieves an absolute max of 300,000 when x equals 3,000. So we have a maximum revenue of $300,000 when we manufacture and sell 300 items, 300 television sets. And we have one other question to ask about this model, namely how do we maximize profit? So we maximize revenue if we produce and sell 3,000 television sets. If I want to find maximum profit, I also need a cost function. So the cost function is 72,000 plus 60x. We want to find the maximum profit. Profit is revenue minus cost. So let's quickly remind ourselves of revenue. Revenue is x times p. We have our price-demand equation up there. Our revenue function is 200x minus x squared over 30. Our cost function is here, 72,000 plus 60x, and profit is revenue minus cost. So our profit function will be the revenue function, 200x minus x squared over 30, minus the cost function, 72,000 plus 60x. We've got to be careful with the distribution of the negative sign. It will be minus 72,000 minus 60x as we distribute this negative over both of those pieces of the cost function. And then 200x minus 60x is just 140x with like terms. And the rest, of course, is minus x squared over 30 minus 72,000. So we have a profit function as a function of x. We'll take its first derivative to find the critical values and then determine if our value is indeed a maximum. So there's our profit function. We need to take its derivative. The derivative will be 140 minus 2x over 30. That's the derivative of the profit function. Set that equal to 0. So 0 equals 140 minus 2x over 30. Or 2x over 30 equals 140. 2x over 30, of course, reduces to 1/15, or x over 15 equals 140. Multiply both sides by 15, and we get x is 2100. Now, how do we determine if that's a minimum or a maximum? Well, I'm going to again use the second derivative test this time. You'll notice the first derivative is 140 minus 2x over 30. So the second derivative is negative 2 over 30, or negative 1/15, always negative. So if the second derivative is negative 1/15, if the second derivative is always negative, we know we have a concave down situation. So we will have an absolute max at our one critical point. So what does this tell me? It tells me that P will indeed achieve an absolute max at the value where x is 2100. But what is that value? We're going to have to plug 2100 back into our profit function. So we have the profit function is 140x minus x squared over 30 minus 72,000. I want to find out what my maximum profit is. That will be plugging the 2100 into the profit function. So P of 2100 is 140 times 2100 minus 2100 squared over 30 minus 72,000, which gives me a P of 2100 of 369,000. Now we know this was a maximum because the second derivative was negative. It was always concave down. So we can conclude that this company maximizes profit when it manufactures and sells a total of 2,100 televisions, and that maximum profit is 369,000. As we see here, maximum profit of 369,000 when the company manufactures and sells 21,000 televisions. Our next problem says the cost per hour for fuel to drive a rental truck 800 miles is given by f of v is 0.03 v squared minus 2.2 v plus 72, where v is the speed of the truck in miles per hour. The other costs total $40 per hour. How fast should you drive to minimize costs? So this is the fuel cost per hour, and we also determine the driver cost is $40 per hour. We need total costs. So let's build that model. Speed times time equals distance. Our speed is v, and our distance is 800 miles. If that's the case, our total number of hours, our time, is 800 divided by v hours. So we have our fuel cost per hour times number of hours. We have our driving cost per hour, $40 an hour times number of hours, to get our total cost. So driver cost is $40 times number of hours, $40 times 800 over v, or 32,000 divided by V is our driver cost for this trip. Driver cost 32,000 divided by V. Our fuel cost per hour, 0.03 V squared minus 2.2 V plus 72. But we need our total fuel cost. Our total fuel cost is the number of hours times dollars per hour. Number of hours times 800 divided by V times all of this. What does that become? 800 times 0.03, 24V, minus 800 over V times 2.2V minus 1760. 800 times 72, 57,600 divided by V. That's our total fuel cost. There's our total driver cost. We want to add those together to get our total costs. Driver cost plus fuel cost, 32,000 over V plus 24V minus 1760 plus 57,600 over V. But these two pieces are like terms, 57,600 plus 32,000. And we get 89,600 over V plus 24V minus 1760 as our total cost. We want to minimize that. There's our cost function. Take the first derivative, negative 89,600V to the negative 2 plus 24 equals 0. 89,600 over V squared equals 24. Multiply both sides by V squared. Divide by 24. Take a square root, and V is 61.1. Let's convince ourselves that that's really going to be a min. I'm going to use the second derivative test again to do that. Our second derivative is negative 2 times negative 1, 2 times 89,600 V to the negative 3, or 179,200 over V cubed, which is always positive, which means the function is always concave up. So we will indeed have a minimum at our critical value of 61.1 miles an hour. So yes, cost is minimized when speed is 61.1. And that will conclude this lesson.